Well, welcome back, and tonight we're going to focus on the second fundamental theorem of calculus. So yes, there are two. We've already talked about the first fundamental several times this year, and tonight, obviously, we're going to focus on the second fundamental. So here is the wonderful definition we need to copy down. If f is continuous on an open interval, then for every x in the interval, here is the second fundamental. The derivative of the integral from a to x of f of t dt is equal to f of x. Did your mind just explode? Well, let me slow down. I'm taking the derivative of an integral. What do you think's happening when you take the derivative of an integral? Keep that in mind. And I'm going to go through a quick example with you. All right, so here's my first example to talk about what just happened. So we're given this function f of x, which happens to be an integral from 0 to x of 2t cubed dt. Notice the integrand when I'm integrating is with respect to t, and this variable is x. That's a big deal. The second fundamental says, let's take the derivative of an integral, and let's see what happens. So let's go about it the long way. Let's actually integrate this thing. So order of operations, we'll integrate this, and then we'll take its derivative. So if I integrate 2x cubed, I get, or 2t cubed, I get 2t to the fourth divided by 4 from 0 to x. So that gets me 2x, well, that's going to reduce to 1/2 x to the fourth. Now the question, the second fundamental theorem says, now take the derivative of what you just integrated. So I just integrated that, and now I'm going to derive it. So if I derive it, I bring that 4 down, so I'm going to get 2x to the third. What did we end up with? Let me zoom in on my work here. Look at what I ended up with, and look at how that compares to what I started with. Well, that's what the second fundamental theorem is saying. When you take a derivative of an integral, you undo it. Now here's the catch. Notice that I did not end up with a t in my answer at all. But in fact, I ended up with the upper bound, which was an x in my answer. So now let me show you the shortcut. So let's star this, highlight it, grab that highlighter. Here's how the shortcut works. To take the derivative of an integral, aka the second fundamental theorem of calculus, you're going to do two things. First, you're going to plug the upper bound in the function. And second, you're going to derive the upper bound. So here's our first example. We want to derive the integral from 0 to cosine of theta of e to the negative t squared dt. So it looks terrible, but this is really a simple idea as long as you follow these two steps. You don't actually have to integrate it and then take its derivative. Just remember this shortcut. So again, first, plug in the upper bound. So I'm going to take the upper bound, which is cosine of theta, and I'm going to plug it into every letter t. So I'm going to say this is e to the negative cosine of theta squared. Now apply step 2. Take the derivative of the upper bound. The derivative of cosine is negative sine theta. And I'm going to multiply those together. So maybe go back in your notes there and say multiply by that derivative of the upper bound. And this is my final answer. It's that simple. You're going to plug in the upper bound and derive the upper bound. If there were 10 t's in your equation, you would plug cosine in 10 times and multiply by its derivative. Example number 2. Take the derivative of an integral. So we've got to recognize that as second fundamental. Of the integral from 1 to sine x of the ln of m plus m cubed dm. Okay, so let's apply the two rules. Take the upper bound and plug it into every letter m. So this is the ln of the sine of x plus the sine of x cubed. Okay, now it's all of that times the derivative of the upper bound. So times cos x. And there you have it. That's the second fundamental. That's what you would get if you were to actually integrate it and then retake its derivative. In our next example, we're going to encounter a tiny little bear trap here, but we're going to talk through it and we won't fall into it. So first off, it's still second fundamental because it says derivative of an integral. That's the dead giveaway. derivative and integral in the same problem. Now, what do you notice that's different from this example, from the previous example, or even from this example to the actual correct notation we wrote out in the beginning there? Take a look, take a look. All right, I think I heard you. You're telling me that these bounds are not in the right order. Notice that the variable, wherever your variable is, has to be in the upper bound when you apply the second fundamental. So you need to make a nice big star for yourself, make a note, write something down. Okay, if the bounds are not in the correct order, you need to flip. The upper bound has to contain the variable. Now, the only deal is when you flip, what do you pull out in front? Of course, you said it, you pull out that negative. Whoops, so my 4 should be down here, and my x squared will come up there, and I'm just going to pull that negative out in front. Okay, so now I can apply the same thing. I'm going to substitute in my x squared. So I'm going to say that's x squared to the 5th. And then I have to multiply by the derivative of that upper bound, so times 2x. And of course, I got to put that negative back in. Now I'm going to clean it up just a tad. Power to a power is multiply, so that's negative x to the 10th times 2x. So I'm going to say that's negative 2x to the 11th. All right, so is the question going to be as straightforward as what we were just doing? Yes and no. When it's multiple choice, that's a good indication of what the question might look like. Here's an example of what a short answer question might look like. So they're given a graph of a differentiable function f. So I'm going to be very clear that this is f on the closed interval 1 to 7. And now they give you a second function, h of x, which is the integral from 1 to x. So you have two functions. You have f and you have h. The first question says find h of 1. So how easy is that? H of 1. Plug 1 into h. So h of 1 equals the integral from 1 to 1 of f of t dt. Well, this is probably one of the easiest answers in the world. If you start at 1 and you move to 1, you've moved nowhere, so you have accumulated how much area? 0. We know when the bounds are the same, we have 0 area. Now here's where the second fundamental comes in. Now they're saying find h prime of 4. So notice h is the integral, and they're telling you to find h prime. So in their own way, they're saying take the derivative of the integral. So for B, h of x equals the integral from 1 to x of f of t dt. They want me to find h prime, so I have to take the derivative of the left side, which means you also have to take the derivative of the right side, because anything we do in math, we balance out when we have an equation. So the derivative of the integral is the second fundamental, so I know h prime of x is equal to, take the upper bound and plug it in, f of x times the derivative of the upper bound times 1. Well, that's easy. So h prime, and I believe they wanted us to plug in a 4. H prime of 4 is equivalent to f of 4. Well, how do you evaluate f of 4? They happen to give you this lovely graph of f. So f of 4 has a height of 2. Let's look at part C. On what interval or intervals is the graph of h concave up? So let's start with the justification. If h is concave up, h double prime is greater than 0. So I have to take two derivatives of h. And remember, h is an integral. So h of x is the integral from 0 to x of f of t dt. So let's take the first derivative, which we already did in the previous question. So second fundamental, plug the upper bound in, times the derivative of the upper. Now I'll take the second derivative, so that's really just f prime of x. And they want me to plug in, I wish I could remember, just when is h concave up. So basically, when is f prime of x greater than 0? That's what I'm looking for. When is f prime greater than 0? Well, you got to talk yourself through it. Who are you staring at a graph of? F. If you want f prime to be greater than 0, you need to look at the slope of f. So what section or sections is the slope greater than 0? Or is the slope positive? Well, I would say in this section, so from 1 to 3, then my slope is clearly negative, and then from 627. H double prime slash F prime is greater than 0. Last part, part D. Find the value at which H has a min. Well, again, start with a justification. How do you justify something's a min? Well, and it particularly says H prime changes from a min would be from negative to positive. Okay, something is a min if H prime changes from negative to positive. Well, we already said twice now, H prime is equivalent to, look back at your notes, what is H prime equal to? F of x. So when does F itself, when does F itself change from a negative to a positive? So if I look at my graph here, well, they're trying to mess with you. Right here, F changes from a positive to a negative, making 5 a max. Does this ever have a relative min? No, but it does have a min on the closed interval. Okay, now, it's probably been a while since we've done this, so it's good review. This is clearly a max, so there's no relative max, which means either 1 or 7 is going to be our min. So let's think about what's happening. From 1 to 5, our function is above the x-axis, so it's increasing. And then 5 to 7, our function decreases. Now in this section, I did way more increasing than I did decreasing. How do I know that? Look at all this area compared to this area. I went up a lot and I only came down a little. This is positive area, a lot of it, and this is just a little negative area. So starting at 1, I have this height, whatever it may be. I have a max at 5, because I went up until 5, and then I came down just a little bit at 7. So I would say, find the value at which x has a min. It has a min at x equals 7. All right, let's try another one. The graph of f consists of a semicircle and 2 line segments shown above. So again, they're telling me that this is f, and now they're going to introduce another function called g. Let g be this integral. All right, so we got to keep them straight. F is the graph, g is the integral. Find g of 3. Okay, so not f of 3, g of 3. So I'm going to plug 3 into this integral. So g of 3 is equal to the integral from 0 to 3 of f of t dt. Well, how do you find that? Well, you integrate f, which is the graph, from 0 to 3. Okay, well, I have a positive quarter circle, so that's 1/4 pi. My radius is 2, so 2 squared, so that's 4, so I would say that's a pi. And then I have a negative, so I'm going to subtract whatever that area is. That looks like 1 by 1, so 1/2 1 by 1 minus 1/2. So I would say this is equivalent to pi minus 1/2. Okay, so find all values on the open interval at which g has a relative max. So notice they're talking about g. G is the integral. I need to find a relative max. Well, how do you justify a max? G prime changes from positive to negative. So I have to go get g prime. And to find g prime, I have to take the derivative of an integral. So are the lights going off? Second fundamental. G prime is equal to, take the upper bound and plug it in, f of x, times the derivative of the upper bound, which is just 1. So really, g prime of x equals f of x. Okay, now, I need f of x, we just said, which is g prime, to change from a positive to a negative. So take a look at f. When does f prime change from positive to negative? Well, hopefully you're pretty good at this by now, and you said at x equals 2. And we already have our justification right there. Part C, write the equation of a tangent line to g at x equals 3. So, at x equals 3, do I know the y value? Now, don't go tell me -1, because that's for f. I need to find g of 3. And guess what? You did that right here. So we already did the y value. It's not pretty, but it's there. So y equals pi minus 1/2. Now I need to get the slope. So I need to find g prime of 3. And I already know g prime, right here, is equivalent to f. So g prime of 3 is really the same thing as f of 3. So g prime of 3 is really equal to -1. Do you see how we're using each other? So now I can write the equation that tangent line, y minus, notice I'm using parentheses, pi minus 1/2 equals -1 times x minus 3. All right, last equation here, or last question. Find the x-coordinate of each point of inflection of g. So let's justify. G double prime changes signs. Okay, do I have g double prime yet? No, but I already have g prime from a previous question. So if g prime equals f, take both of their derivatives each side, g double prime must equal f prime. So I need to see when g double prime, which is the same as f prime, changes signs. Happen to have a graph of f, and I need f prime, so I'm going to look at its slopes. When does f prime change signs? When do the slopes change? So these slopes are positive, now they're negative. Bam, right at x equals 0. These slopes are negative, they don't exist, but they're negative again, so 2 is nothing. These slopes are negative, these slopes are positive, so slam bam, we got another one at x equals 3. So I would say there's 2 points there. And look, we already justified our answer because we've talked a million times this year to come up with a game plan first, and you've got half the work done. Well, that does it for second fundamental. If I went too fast, slow down, go back, rewind, but hopefully it's a pretty friendly topic. We'll see you tomorrow.